Hello there, my name is Charles Wasfani. Welcome to our first presentation on functions of complex variable. The aim of this presentation is not to develop the whole theory of function of complex variable, but just to give you a brief feel of how functions of complex variable work. But first of all, we're going to revise recap the concept of a function. Now, talking about a function, we recall that if we are talking about function, normally let's refer to a function of single variable. We always think of a situation where we've got two sets, let's say set x and a set y. And the function normal will be kind of a rule of assigning values of x to values in y. So now if we've got a value in x, we can assign a value in y, which you can call y equals to a value of the function at x. So a function will be acting between two sets. But talk about the concept of function as such, we must understand that not every action of this type results in a function. So we would say such kind of an action or such kind of an assignment is a function if, when given a value of x in the set x, which we call the domain of the function, we can assign a unique value, as only one value y in the set y, which we call the value of the function at f of x. So if we write here y equals to f of x, what you must understand is that x is known as the independent variable, it's independent variable of the function, and on the other hand y is the dependent variable, meaning that to get the value of y, we first of all go to pick a value of x, then evaluate the function according to the formula or the expression of the function to get y. So we say y is a function of y depends on x. And sometimes we talk of f mapping the set x to y, and we need to see not here that the x can be taken as the domain of the function f, and which you can write briefly as d sub f. And on the other hand, y is called the codomain of the function f. Now, we remember in our previous courses in mathematics, we dealt with functions of single variables. In this case, f is a function of single variable. A good example of that is the function the well-known function like the parabola, like y is equal to x squared, which we can plot on a system of coordinates, in this case on an xy system of coordinates, where we've got x horizontal line there being the set of real numbers, and the y here, the codomain being the set of real numbers. So what we know is that when you plot this graph, we get a graph more or less of this shape. So what you can see here is that the values of this function start from 0 going upwards. In other words, that we call the values of y greater or equal to 0, y being a real number, we call those values, we say they belong to the range of the function f. Now, we also recall that a function is a kind of an input-output system. In this way, using a flow diagram, we can consider that this is a system. Now, by system, we mean a collection of components or units which are connected in a certain way to perform a task. And I repeat there, I'm saying a task. In other words, if you put an input here, we assign an input here, then we expect to have an output there. So, like we've said, if it's a function, it should behave in such a way that if you put an input, you should get here a unique output y. That's what the function. Sorry. So, in other words, a function can be any process which work in a similar way. You are defining a function that given input, you get a single output. So, for all along, our functions in the earlier courses, our x has been a real number, and then when you say f of x, evaluating the function, we're also getting a real number, and such functions we call them functions of real variables. Real from real numbers. Now, we also remember that we also studied what we call complex numbers, and the complex numbers are denoted by the letter z. Let's say z is a complex number, and the collection of complex numbers, or the set of complex numbers, is denoted by c of this nature. And you recall that z is equals to x plus imaginary unit I multiplied by y, where x and y are actually real numbers. And I hope you remember that these numbers, we represented them on a system of coordinates as points. Let's say we've got a point there, which has got coordinate x and y. And expressing this point as a number or as a composite number, we say this is x plus I, y, where I represent the imaginary unit along the vertical axis. And then on the horizontal axis, we've got our usual real numbers. Right. So now, at this point, I'll encourage you to recap the theory of for complex numbers, and make sure that you are able to operate with complex numbers, as our functions here are going to be functions of complex variables. Now, important in function is the fact that we could, with real numbers, we could plot functions, otherwise the graphs. We could plot functions in terms of graphs. For example, we could have a function. In this case, I'm not really interested in the expression of function, but we could be able to draw a graph on the system of coordinates like that, and say this function, the graph, this is a function y is equal to f of x. In this case, you must understand that wherever you've got a point there on the graph, that point has got a coordinate x there and a coordinate y there, but y is equal to f of x, which means the coordinates of this point is actually x, comma, f of x as a pair. Okay. Now, when you come to functions of complex variable, this kind of representation is a bit challenging. So what I'm trying to say that it's not very easy to plot functions of complex variable like we did with functions of real variables, especially single variables. Now, in functions of complex variables, we've got a situation like this. Let's say we've got a plane here, which we can call a z-plane. Now we can call this, let's say this is a domain of a function. Let's say we call the function z, sorry, not z, let's use omega. Let's say the function is omega equals to f of z. What is the expression? That this function is acting on a complex variable z and delivering a complex value omega, which can represent that way. So what actually happens here, now talking about in terms of mapping, this function will be mapping a region or part of the complex plane to another region on the omega plane. So let's say maybe we've got a region here which covers this point, any shape. Those are points in that region. So what will happen? A point z here will be evaluated and give us a point omega there, and this region could be transformed to another region of a different shape from what it was there. Then we're talking about this as the image of this region on the omega plane. And you remember also that complex numbers represent them in such a system which we call an Argand diagram. But in this case, this would be kind of a graphical representation of a complex function. Now, these mappings actually have also their long theory and how to do them, but we're not to engage ourselves with that now. What I'm going to do next is to give you an example of a complex function and then discuss it there with an aim of focusing on the structure of a complex function. Let's say here an example. We've got f of z equals to z squared. Now it is almost the version of our parabola in complex variable, but we shouldn't think of this as a parabola. So now, remembering that our z is of this nature, what we can do now, we can say omega is equals to f of z equals to z squared. Now, substituting z in terms by this expression, we can say this is equals to x plus I, our imaginary unit, y squared. Now, at this point, what we need to recall our binomial expansions of expression like a plus b squared, which we all know that this will give us a squared plus 2ab plus b squared. Now, identifying our a with x and our b with I, y, then we should be able to see that this will give us x squared plus 2x multiplied by I, y plus I, y squared. Now, if you remember complex numbers, we remember that the square of the imaginary unit is actually equals to minus 1. So what we're going to have, we are going to have I squared, y squared, which this expression is going to end up being x squared minus y squared, where minus 1 here, it comes from I squared, plus 2xy I, meaning this is the imaginary part of the system. Now, what's going to happen now in the, which means this will be expression giving us omega on the omega plane. So in this case, what we can do is we can say this is our u, and as you can see, a u is actually an expression of x and a y, and this part here will be our v, and also is an expression of x and y. And then we need to label here I to say v is the imaginary part of the function. Now at this stage here, we should actually learn that now in a complex function f of z will always come in with the same structure of complex numbers. In this case, u as u function of xy plus imaginary part v function of xy. And this is very important because when you get to differentiation, it will be very important to be able to identify the imaginary part and the real part of the function of complex variables. Now, evaluating these functions is not very different from what we did with functions of real variables, as long as you know how to evaluate functions. Let's say, for example, evaluate we just discuss one value and then you do the rest. Let's say if I evaluate 1 f at 3 plus 2 I, and number 2 evaluate f at 0 f at 2 this is number 3. 4 evaluate f at minus 2 minus 2I, and lastly 5 evaluate f at 3 plus 3I. Please evaluate this and try to plot your values on an Argand diagram on the omega plane. In this case, on the omega plane. Here we're talking about omega plane because f of z is omega. Now the second example, the second example which is going to follow now, I'm going to try to sort of take an example of a function of complex variable and see how it acts on a region or something like a line, and see how the image would look like. Okay, let's say we're given a function omega, which is 2z plus that, and we've got our region. In this case, we're going to take it as a line 3x plus 1, and then we want to see that by mapping this line via this function, what kind of an image do we get? So let's start this way. We have here that omega is equal to f of z equals to 2z plus 4. Please notice that this line is a line on an xy coordinate, and the points on the xy coordinate can be identified complex numbers. So each point on this line is some kind of z. So solving this problem, what we need to do is, first of all, we must know that omega is written as u plus I v, which in this case we are told that this is equals to 2z plus 4, which is our f of z. Now replacing z with our form of z, which is z equals to x plus I y, we're going to have this as 2 brackets x plus I y plus 4. Now here this takes us to 2x, removing brackets, plus 4 plus I multiplied by 2y, which in this case what we can say is that u is equals to 2x plus 4 and v is equals to 2y. Now next, what we can see now, what we need to do now, we can write x here in terms of u, which is going to come up as x equals to half u minus 2. I hope you can see how you can do some algebraic multiplication here, making x up a formula that takes you to that. And on the other hand, we've got y is equals to v divided by 2, by dividing both sides here by that. So what then it means is that y equals to 3x, our line on the z plane, plus 1 is then transformed to v, which is our y, replacing y there, v over 2 is equals to 3 brackets half u minus 2, which is our x, plus 1, which in this case is mimicking the equation there. Then simplifying this expression, we see that we've got v equals to 3u minus 10. Now, if you look at this last expression here, 3u minus 10, you can see also that this is an equation of line. Never mind that is u, but if you say y is equal to 3x minus 10, we know that this is equation line. But now we read it in this way because now we are mapping this to the omega plane, where our x-axis is u and the y-axis is given by v. So that is on the omega plane. So that's what we get there. So what you can do now is to try to represent this line, which was given as 3x plus 2y on the z plane, and then its image via this function is what we're given here as v equals to 3u minus 10. Then you can compare the two and see how the line has been transformed. But what we can gather here at more immediate is that this line 3x plus 1 is transformed to a line, sorry, y is equal to 3x plus 1 is transformed to a line v is equal to 3v minus 10. So the change actually has been in the intercept on the vertical axis. The gradient is maintained. Now plotting these lines on the corresponding planes, let's say here we are plotting y is equal to 3 x plus 1. So we note that this line cuts the x-axis, the y-axis at 1. Let's take these divisions made by the dots to be 1 unit. In this case, what we're going to get here, we're going to get 1 there. And the gradient is 3. In this case, the gradient is 3, meaning 3 over 1. In other words, we have here y1 minus y2 over x1 minus x2, our gradient, which means we run horizontal 1 and vertical 3. So this is going to be 1, then vertical 3, 0, 1, 2, 3. Then we know that that point there is also on the line. Now, what we're going to have here, we're going to have a line which we can plot this way. But line must pass through this point, then we rotate this a bit, then we get the line there. So this is the line y equal to 3x. Now, on the other hand, we saw that this line via the function f mapped to the omega plane. In this case, function f, we know the function f omega is equal to omega 2, it was 2z plus 4. So this is f of z equals to 2z plus 4. And what we got here is a line v, which is our vertical axis, equals to 3 u minus 10. Now, in this case, what we see that the intercept on the y-axis is at minus 10. So maybe we need a different scale here. We can say 2, 4, 6, 8, 10. Let's say we've got our minus 10 here, which is our cutting point for the line. And you can see that if our v is 0, if we set our v 0 here, we will see that u is going to be equals to 10 divided by 3, which should give us 3 comma something. So if you count here as along the scale, say 1, 2, 3, then we've got an intercept on or 0 on that at that point. Now what we have now, we can now plot a line which goes through this point up to there in that direction. So what we can do here, we can do the same thing and adjust this line a bit, and that's what you get. So now what we can see now, as you can see, this line here was going through the first, the second and third quadrant, and this side we've got the line going through the first, the fourth, and third quadrant as the image of that line on the z plane. So now this is what in complex analysis they call mappings via complex functions, but we're not going to go into this a lot. I just wanted to give you a feel of how a function of a complex variable x, and how you can sort of have an example of a graph of a function of complex variables. Otherwise, this is enough for introduction of functional complex variables. The next presentation will be on how to differentiate functions of complex variables. Thank you for listening.